Hello and thank you for participating in the Northwest Territories and Nunavut Geoscience Symposium. My name is Tim Ensom and I'll be speaking about the thermal regime of riparian environments in continuous permafrost in the Western Canadian Arctic. I'm a Yellowknife-based PhD candidate working with Steve Kokelj of the Northwest Territories Geological Survey and Philip Marsh of Wilfrid Laurier University. Riparian systems are an important and dynamic component of the landscape, and this work is being pursued in the Beaufort Delta region of the Northwest Territories. The communities, transportation infrastructure, land use, and variability in the physical landscape make the region an important focus from a scientific and applied standpoint. This is primarily the Inuvialuit settlement region north of Inuvik and Aklavik, and the Gwich'in settlement area to the south. There is a latitudinal gradient in climate and ecological conditions, and mean annual air temperature decreases from about -8 degrees Celsius in Inuvik to about -10 in Tuktoyaktuk. In the southeast we have spruce forest, with tall shrub tundra just north of treeline, and dwarf shrub tundra further north in the Tuktoyaktuk coastlands. Continuous permafrost underlies the region, and to the east of the Mackenzie Delta, mean annual ground temperature is around -3 degrees Celsius in taiga forest and about -7 in dwarf shrub tundra. The regional climate has been warming since the 1970s. We know that large rivers in the Western Canadian Arctic may continue to flow to some extent all winter, and this early 1980s photo on the northern Mackenzie River provides a good example of evidence of sustained winter runoff in a small river at its confluence with the Mackenzie. Winter water movement observed in smaller watersheds and the riparian corridors that drain them highlights the importance of advancing our knowledge of the thermal regime of these systems. The photo here shows an overflow event just west of the Inuvik to Tuktoyaktuk Highway, or ITH, about 30 kilometers south of Tuk, occurring when the air temperature was -30 degrees Celsius. The watershed contributing to the site of the overflow is about 3 square kilometers. Streams or riparian corridors that are conducive to winter water movement can represent safety and management challenges for infrastructure like highways if flow persists for long enough in winter to freeze and block culverts, such as this site at kilometer 30 on the ITH. Impoundment of spring freshet by blocked culverts or off-ice can lead to embankment scour or even washout. These observations and other gaps in knowledge about winter hydrothermal dynamics in riparian systems have led to these research questions. In continuous permafrost, the movement of water on the landscape during winter is linked to thermal regime. We need to understand temperature controls and dynamics better in order to project how a warming climate and changes in precipitation will modify the riparian thermal regime. While we know about runoff from some larger regional streams during the open water period, we don't know much about the amount or timing of winter runoff in small systems. This presentation will focus on the first two questions. One of the main controls on riparian thermal regime is snow cover. On tundra, deeper snow accumulation can occur in streams and riparian systems than on uplands because of entrapment of blowing snow by riparian vegetation. This can insulate these systems better, delay the freezeback of the riparian active layer in the early winter, and therefore prolong the drainage of water out of small watersheds in winter. Recent work is showing that vegetation is becoming taller and more pervasive on the tundra in this region. In this figure by Fraser, Lance, and others, we see, in green, areas where the normalized difference vegetation index increased between 1985 and 2011. If taller vegetation is increasing disproportionately in riparian environments, there's potential for greater delay of the refreeze of the active layer in these systems. Since the study region also includes taiga forest and a transition to tundra, there's potential for different thermal responses to this change outside of tundra environments. The thermal regime of regional watercourses at multiple scales has been investigated for decades. Mackay described the mean breakup and freeze-up dates for the Mackenzie Valley and the cross-sectional form of channels in his 1963 memoir. Michael Smith investigated Mackenzie Delta channel, lake, and bank thermal regime in the 70s at a site characteristic of the delta. The thermal regime deep beneath the beds of Caribou Creek and Wrangling River were explored by Vankevich in the late 1970s, in part due to interest in highway infrastructure and off-ice. Anderson described the distribution and recurrence of icing activity along the new Dempster Highway and at sites along the proposed route of the ITH in the late 70s and early 80s. Stevens and others investigated thermal regime beneath a series of streams along the route of the proposed Mackenzie Gas Project in 2009 and 2010. This work focused on the thermal regime of stream beds and on comparing upland and valley bottom ground thermal regime. This was accompanied by graduate research on the thermal regime of channels in the Mackenzie Delta. The investigation of the present thermal regime in riparian systems between the Northern Dempster Highway and Tuktoyaktuk has expanded since 2017 with the collaborative Permafrost Sentinel program and related activities. Parts of the ground temperature monitoring network established within the embankment and structures along the ITH as early as 2013 to monitor thermal performance also informed the research program. While some riparian sites have only diffuse drainage, many have two sub-environments including a riparian margin above the bankful elevation but within the vegetated corridor and a stream channel. Havokpak Creek, shown here, is in taiga forest near the Inuvik Airport and provides an example of a system where temperature is being monitored on and beneath the surface in the riparian margin and also on and beneath the stream bed. The black dots represent thermistors. A series of riparian sites has been instrumented this way, and we can compare upland and riparian environments with respect to their surface temperatures. At ITH kilometer 103, there is an instrumented riparian system with an 8 square kilometer contributing watershed. This is the west-facing view from the highway of the creek at kilometer 103, which flows east and under the road in a channel identified approximately by the blue line. By this date in mid-April 2019, there was about half a meter of ice in the channel and just over a meter of snow on top of the ice, making the landscape look flat. This figure shows surface temperature for the hilltop, streambed, and riparian margin. Although we have only 3 years of data, it's apparent that in some winters the riparian system remains much warmer than upland terrain, but that the riparian margin can also get just as cold as the upland. Winter 2020 was especially cold, with much less snow than normal, and the streambed froze that winter. Another potential cause for the colder streambed that season would be less flow than usual at the time of freeze-up. Although interannual variability in snowpack can highlight the influence of snow on riparian temperatures, the ITH introduces within-season spatial variability in snow cover that we can examine. There are 8 bridges along the highway and several reduce snow accumulation on the streams underneath. Creek 18, draining a 28 square kilometer watershed just north of treeline, provides a good example of this effect. The brown overflow ice visible here is recurrent at certain ITH bridges and is a common problem facing northern infrastructure. By instrumenting riparian systems upstream and downstream of several bridges, as well as under the bridges, we can begin to describe the thermal effect of intercepted snow caused by the bridges. The top figure here shows temperature on the top of the streambed upstream of 4 bridges along the ITH for the past 3 years. The lower figure shows streambed temperature underneath the bridges. Streambeds generally get colder during winter under the bridges with the smaller contributing watersheds. Those sites are represented by the yellow, orange, and green series here, and contributing watershed areas do not exceed 30 square kilometers. Creek 35, shown in purple, is about 130 square kilometers. Although we don't have the most recent year of data there, streambed temperature does not appear to be strongly influenced by the absence of snow under the bridge at that site. The colder conditions at the upstream sites at Creeks 3 and A3 this past winter may be the result of reduced insulation from snow on the landscape. The cooling effect of bridges likely occurs as follows. This is a cross-section of a bridge over a stream, and in this slide we have a thawed active layer and a thawed stream flowing in late summer or fall. In early winter, if snow cover doesn't accumulate on the stream because of the bridge overhead, then the stream can freeze to its bed or even partway to the permafrost table below quite quickly. Since the stream and substrate can't provide a conduit for water to drain from the watershed, this freeze dam reduces flow in the stream downstream of the bridge, which means less advected heat is available downstream of this thermal disturbance. The temperatures of streambeds downstream of the bridges are colder than streambeds upstream of bridges. This may be due in part to the reduction or shutoff of the advected heat supply as a result of the freeze dam under the bridge. The role of advected heat in the thermal regime of riparian systems of this size may be limited, however, because freeze-up in the streambeds downstream of bridges does not clearly lag behind freeze-up under the bridges. Another cause of the warmer streambeds upstream of the bridge-induced thermal disturbances may be the latent heat effect of impounded water. If we consider larger streams in the region, data from past work and current activities suggest that heat advection from stream flow might be a more important component of the thermal regime in larger watersheds and might also affect the surface thermal regime of streams differently than the ground thermal regime deeper beneath streams. This figure shows annual mean temperature on the top of stream beds versus contributing watershed area, which is likely to represent long-term available advected heat. Although we won't be exploring these data statistically here, these results suggest that other factors also influence temperatures at the top of stream bed. The horizontal axis is logarithmic and represents watersheds from the 0.3 square kilometer Big Bear Lake watershed near Trail Valley Creek to the 1,600 square kilometer Campbell Creek watershed that drains into the east channel of the Mackenzie Delta, 25 kilometers south of Inuvik. Temperature measurements from 7 to 8.5 meters below stream beds suggest a more clear positive association between mean temperature and contributing watershed area. Although the temperature measurements beneath riparian and stream environments with watersheds larger than Hans Creek are from investigations a decade or more old, it is reasonable to assume that these mean values would more likely be higher than lower if measured now, and that the positive association between watershed area and mean temperature would still be apparent. The size of the watersheds or the depth of temperature measurements likely make these older values less sensitive to interannual variability and therefore still relevant. The relation here, if representative, would suggest that the top of permafrost is very likely deeper than 7 to 8.5 meters beneath stream beds if the contributing watershed exceeds 300 square kilometers. Figures by Vankevich suggested that permafrost was not yet present at the maximum instrumented depth of 14 meters beneath Caribou Creek or Wrangling River. In addition to snow insulation and contributing watershed area, latitude has a known influence on annual mean ground temperatures. Kokelj and others presented a synthesis of mean ground temperatures in the region to show their association with latitude between Inuvik and northern Richards Island. Hollow triangles represent undisturbed near-surface conditions at about 1 meter, and hollow crosses represent undisturbed deep conditions at 10 meters. Filled symbols represent disturbed conditions. We can use this figure to contextualize the riparian and stream channel thermal data for corresponding depths, added here in green and red. The near-surface stream channel or riparian temperatures plot near or above the transition from undisturbed to disturbed sites identified by the authors. The deep temperatures beneath stream channels draining larger watersheds plot among the disturbed sites, while the deep temperatures beneath the sentinel riparian sites with the small watersheds plot among undisturbed sites. The association between latitude and annual mean temperature can be explored for the riparian and stream sites alone. There is no clear relation between latitude and temperature at the top of stream beds. In addition to advected energy and its likely association with watershed size, the relation between top of stream bed mean temperature and latitude in this region is also likely affected by the latitudinal gradient in vegetation. Riparian systems in the taiga forest and transitional region may be sheltered by tall riparian vegetation and not accumulate wind-blown snow to the same extent as tundra sites. At greater depths, it's less likely that local snow accumulation would modify the influence of the latitudinal climatic gradient appreciably. Contributing watershed area may be the most important factor determining the thermal regime at these depths beneath stream beds. For the small riparian systems, latitude is more likely to influence annual mean temperature. To summarize, riparian systems in continuous permafrost have distinctive thermal regimes from proximal upland terrain, and understanding this regime is important for understanding winter runoff. Second, the local distribution of snow is likely to be the most important factor influencing spatial and short-term interannual variability in the shallow ground thermal regime of riparian systems with small contributing watersheds. Finally, as watershed area increases, advected heat becomes more important in influencing thermal regime, particularly at greater depths beneath riparian surfaces or stream beds. I would like to acknowledge in particular the field support of the Inuvialuit Land Administration Permafrost Environmental Monitoring Program for the past 2 years. And of course the following individuals and organizations for their support. Thank you for your attention, and I'd be glad to speak with you if you have any questions.